All right, hello, chemistry class. This is Coach Jeans talking to you. Today we are still in gas law, so it's Unit 7 in your composition notebook, and we're going to be talking about the combined gas laws. You should have a calculator out, of course, your composition notebook, so you can jot these notes down and then be ready to work out these problems. If you don't have that, just pause your video and come back. All right, so far we have talked about Boyle's Law. Boyle's Law deals with pressure and volume. Remember, this was the inverse proportion. So it basically says that if one goes up, the other goes down. If you increase the pressure by 2 times, then the volume goes down by 1/2. Then we have Charles's Law. Charles's Law deals with volume and temperature. If one goes up, the other goes up. So if you double the temperature, you double the volume, and vice versa. Then we have Gay-Lussac's Law. Gay-Lussac's Law deals with just pressure and temperature. And again, it's directly proportional. If you double one, you double the other. Double the temperature, double the pressure, and vice versa as well. Well, now what we have here is we have what we call the combined gas law. And in the combined gas law, what we do is we put all 3 of those laws into one place. And as you can see here, what we do is we put it's P1 times V1 over T1 equals to P2 times V2 over T2. Now, we also could have our N in there. Remember the 4 factors that we talked about. We have pressure, volume, temperature. What does N represent? N represents the number of moles. And so we could talk about the number of moles. We could have N1 here, and we could also have N2 right there. But we're really going to just kind of ignore that for this section because we're assuming that we have the same amount of gas at the beginning and the end. All right. Later on, we'll bring N back into it and talk about what happens with the number of moles and so forth. All right. Now, still kind of getting used to this little new way of doing things here. Okay. So we go on to an example problem. Example number 1. So jot this example down in your notebook and pause the video, and then we'll come back and work it. Okay, so you've jotted this example down in your notebook, and it says that you have a 2.30 liter balloon that's at 15 degrees Celsius, and it's 570 millimeters of mercury. So we've got a volume, we've got a temperature, we've got a pressure. It's taken to the top of a mountain where it is negative 15 degrees Celsius, and it is 425 millimeters of mercury. What is the final volume of the balloon? So as you can see here, not just one thing changes, not the temperature changes, but also the pressure changes as well. And so how are we going to deal with that? Well, we're going to deal with that using our combined gas law. So again, in all word problems, I recommend that you identify the given. First of all, you have 230. All right, 230. Let me go back to that slide. You have 230 milliliters. All right, liters. And so 230 liters, what's that? Well, that's going to be your V1. So you want to jot that down, 230 liters, all right? Now, and it says it's at 15 degrees Celsius, so that's temperature. So that's going to be your T1, 15 degrees Celsius. Now, remember what we need to do is what? Add 273, okay? So we're going to go ahead and add 273 to that, so that's going to give you 285, okay, for kelvins. All right, sorry about that line right there. Okay, and then we're going to have 570 millimeters of mercury. So that's going to be our P1, 570 what? Millimeters of mercury. All right, let me go ahead and get rid of that line right quick here. All right, and it seems like I'm doing it a lot with this pen. Okay, so 570 millimeters of mercury. Now, then we take it to the top of a mountain. Well, what is the new temperature? So that's going to be our T2, all right? So our T2 is going to be what? Negative 15 degrees Celsius. So it's pretty cold up there on top of that mountain. We still need to add 273 to that. So we get our calculator, or you can do that in your head probably. So 273 plus a negative 15. 273 minus 15 gives you 258. 258K. All right. And then the new pressure, P2, is equal to what? 425 millimeters of mercury. Now be careful with these problems. Make sure that you always convert your temperatures over to kelvins and make sure that with your pressures that they are the same. All right, so if a problem gives you the pressure of millimeters of mercury and then it changes on you and tells you in atmospheres, you've got to convert that over. And just remember your conversion factors at 1 atmosphere equals to 760 millimeters of mercury, which is equal to 101.3 kilopascals, which is also equal to 14.7 pounds per square inch. All right, so we can use the combined gas law because we've got two things going on here. So what do we have? We have P1, all right, times V1 over T1 is equal to P2 times V2 over T2. So now we're going to substitute our values in. We've got a P1 of 570. 570 what? Millimeters of mercury. All right. We're going to multiply that by our V1, which is 230 liters. 230 liters. Actually, I'm going to change this over a little bit. Erase that right quick. All right. All right, so this is all over T2. I'm not going to have much room, so I'm going to squeeze it in over here. So coming over here, this direction right there, our P1 again was 570. All right. And our volume is 230. Okay. That's going to be over our T1 in Kelvin is 285. 285 is equal to what? Well, it's equal to our P2. We know what that is. That's 425, which is going to be times our V2. We don't know what V2 is, so that is our unknown, over our T2, which is 258. Okay, all right, 258K. All right, so now what we're going to do, we're going to employ a little bit of algebra, and shortcuts you can just cross multiply. So the 238 is going to come to the top, the 425 is going to come to the bottom. All right, so then what we're going to do is we're going to solve for V2. All right, so we take our calculator out, and we're going to take 570 times our 230. Okay, because that's our hang on a second. All right, 285. Yes, 285. That's what that's supposed to be right there. I don't know where that came from, but that is supposed to be 285. All right, so again, let me try to straighten this out a little bit, make it a little bit clearer. Sorry for the messiness. 285. All right, a little bit better. Not a ton, but okay. So here we go. 570 times 285 times what? Well, remember the 238 comes over there. Actually, 258 times 258. Where'd that came from? That came from right here. 258K. All right. And so then that's going to be equal to what? Well, 570 times 285 times 258, and then hit equals, okay? And then you're going to hit divided by what? 285 divided by again 425. Remember, they're both on the bottom, so it divided by both times, all right? And so I'm getting some kind of odd type of number here. So let's try again. 570 times 285 times 258. Okay, divided by 285 divided by 425 equals. Okay, that gives me a better number. So this volume is going to be what? 346.02. We'll go 3 significant figures. And since we're in volume, we're going to use liters because that's what our problem gives us to us. We could have milliliters or something else, but this would be our answer. All right. And so the volume is going to actually increase quite a bit because of the temperature change, and the pressure is going to change quite a bit. So the pressure has a bigger difference than the temperature change on that one. All right, so let's go on to the next problem here. And we have an additional problem. This one says, all right, wait a minute, we're on the same one. Having a little technical difficulties this morning. Okay, example number 2. So jot this example down and pause the video and then come back. All right, sealed metal container, which is 250.0 milliliters at 1 atmosphere at 25 degrees Celsius, is placed in a furnace that's 500 degrees Celsius. What will be the final pressure? Okay, So we're given some information. We're given a V1. Okay, go back to this thing again. All right. So we're given a V1 as 250.0 milliliters. Okay. We're given a P1 of 1.0 atmospheres. We're given a T1 of 25 degrees Celsius. So we're going to go ahead and add 273 to that. So that gives us 298 K. And then we're placed into a furnace at 500. So it's going to be T2. All right, is 500 degrees Celsius. So we still need to add our 273 to that. So that's 773 K. Now, what is our P2? Well, our P2, we're going to assume is the same as our P1, all right? So P2 equals to P1, which is equal to what? 1 ATM. And the question says, what will be, actually, no, I'm not thinking correctly. It says, what will be the final pressure? So we're trying to find P2, right? Okay. So we're going to assume again that it's a sealed container. So our V1 and our V2 will be exactly the same. So what we have P1 times V1 over T1 equals to P2 V2 over T2. All right. Now, what remains the same? Volume remains the same. So if volume is the same on both sides, then we can go ahead and cancel that out. We don't need to worry about volume. So what does this look like? Okay, that looks very similar to something that we've already dealt with. Gay-Lussac's law, P1 over T1 equals to P2 over T2. So really this is a Gay-Lussac's problem, but we're going about it by looking at the combined gas laws. All right, so now let's do our problem. We have 1 atmosphere. We don't need to worry about volume, so we're going to go over T1, which is 298. Okay, equals to what? P2, well, we don't know what P2 is. That's our unknown, over by T2, which is 773. All right, so we're going to cross multiply. So we're going to go 1 times 773, okay, 1.0 times 773, which of course is 773, okay, over what? 298. 298. So let's do that on your calculator. Basically, you're just going to take 773 divided by 298, and you get a P2 of 2.593. So we'll go 2.59. Okay, and then what's this going to be in? Well, it's going to be an atmosphere. So be sure to put your final unit there. I could show you how that all cancels out. All right, but for this problem, you could just kind of look at it that way. Okay, let's take a look at another one here. All right, example number 3, a 3.3 liter sample of nitrogen at 0.81 atmospheres at 22 degrees Celsius is compressed to a volume of 1.5 liters and a pressure of 2.5 atmospheres. What is the final temperature of the nitrogen? So jot that problem down, pause the video if you need to. Okay, so here we have it. We have our V1, again, identify our unknown, our givens, and then identify our unknown. We have a P1 of 0.81 atmospheres. We have a T1 of 22 degrees Celsius. 22, let's see, we'll get a little bit better shot here. 22 degrees Celsius. All right, let's see here. Let me erase that. Looks like a mess there. All right. So T1 is equal to 22 degrees Celsius. All right, so we're going to add our 273. 273. Okay, so that's going to be what? 295. Okay. All right, and then what else do we have here? Well, it says it's compressed to a volume of 1.5 liters, so that's a new volume. So that's our V2, 1.5 liters. Okay. And a pressure of 2.5 atmospheres. So our P2 equals 2.5 atmospheres. All right. Now, what is the final temperature? Okay, so P1 times V1 over T1 equals to P2 to V2 over T2. All right, so let's plug in our values. Our P1 is 7.81 atmospheres, pretty high pressure. 7.81. Okay, times our V1, which is 3.3 liters. Okay. Divided by our T1, which is 295. Okay. That's going to be equal to our P2, which is 2.5, times our V2. V2 is 1.5. Okay. And that's going to be divided by our T1. And that's what we're trying to find. Or excuse me, T2. So that's our unknown. All right, so we're going to cross multiply, okay? So we need to get the T2 isolated. So we're going to multiply it up here, bring it up to the top, okay? We're going to bring our 2.5 times our 1.5 to the bottom, down here, okay? And then we're going to bring our 7.85, all right, down here to the bottom, okay? So that's going to actually, let's see. All right, let me start over on that problem and correct a little place that I was going the wrong direction on, okay? So we'll take a look at this one. All right, so here's what we're going to do. We're going to take rid of this right here, this right quick. Okay. Back to my problem here. And having a little technical difficulties. Okay, here we go back to my problem. All right, so we've got our given. So now, again, let me go back through this so that we will get this straight in our head, all right? So P1 over V1 over T1 equals to P2 V2 over T2. All right, so now plug our values in just like we had before. We're going to have 7.81 atmospheres times our V1, okay, 3.3 liters. Okay. Divided by what? Our T1, 295, equals to our P2 of 2.5 times our V2. All right, V2 was 1.5 liters. V2, 1.5 liters. Over our T2. Okay, so we got to isolate the T2, like I said. So that T2 needs to come up here to the top right there, all right? The 295 needs to be cross multiplied here. And then the 7.81 times 3.3 needs to come down here. All right, so here's what we end up with. We end up with T2 is equal to 295 times 2.5 times 1.5, and that whole thing should be over 7.81 over our times 3.3 on the bottom. Okay, so now we're ready to take our calculator. We're going to put this through. We're going to say 295 times 2.5 times 1.5 equals, and then we're going to get divided by 7.81, and then divided by again, because 3.3 is on the bottom. So divided by 3.3. All right. So again, it's 295 times 2.5 times 1.5 divided by 7.81 divided by 3.3. And your new temperature is 42.9 K. So pretty cold temperature there. All right. So hopefully you followed that. Sorry for the pause and the long delay on that one. And we'll be working some more examples of these in class. So hope to see you next time.